Hey there, everyone. Good morning. Happy Thursday. We'll go ahead and let folks start filtering into the Zoom room here. Thank you for joining us for our Think Like an Engineer webinar. We are going to go over a lot of exciting new information with you all. As you get settled in, I wanted to encourage you to navigate to the bottom of your Zoom window and locate the chat button. It'll be right at the bottom. It looks like a chat bubble. It says chat below it. If you click that, you'll be able to chat to everyone. And I do mean everyone. Make sure in the little to section, you click that you're chatting to everyone. We are going to be answering your questions during the webinar. So if you send it to just us, it's going to look like we're talking to ourselves. And that's why I'm asking you to make sure that is set to everyone so that everyone knows what questions are being asked. We can share the wealth. And to get things started, I would love to hear you let me know what the most exciting thing you have done or are doing this summer. Let's see, in yesterday's webinar, one of our presenters recently became a grandfather, so that's very exciting. I know people have summer school going on, there's some trips happening, so please make sure, let me know. Drop in the chat, what is the most exciting thing you have done or are doing this summer? And make sure that chat bubble is set to everybody. Let's see. Very cool. So we have one of our participants is taking the dogs to the lake. I love that. Tom and I were just talking about a lake vacation. So it sounds like everyone's got awesome outdoorsy plans. What else are you all up to this summer? Looks like folks are still typing. Oh, cool. One of our attendees toured Biosphere 2 in Arizona and the Arizona State University Solar Fab Lab. That is so cool. Well, you are in the right place. So very cool. Science Museum in Oregon. Oh, was that OMSI? We love OMSI. Visited my son in Phoenix. Oh, that's very cool for his couple shower. Exciting. All right. Well, it looks like we're 2 minutes past the hour. So to make the most of our time together today, I just wanted to share some housekeeping items. First and foremost, I do want to let you know that you will receive a recording of this webinar. It typically takes us about 3 to 5 business days to have that ready. And as soon as it's ready, we will email it out to you. So keep an eye on your inbox. It will also be on our website and on our YouTube. So you'll have lots of access to that. In that email with the recording, you will also get a link to our resources folder. It's going to have today's presentation, some experiments that you can do, and I'm going to drop that into the chat as soon as I'm done talking as well. And the second piece of housekeeping I mentioned earlier, we will be taking questions during today's webinar, so please feel free to drop your questions in the chat. Our fantastic presenter, Fran, is going to have an eye on the chat, so please let us know if anything is sticking out to you, if you want some clarification. We'd be happy to help. If we happen to not get to your question today, you can absolutely reach out to us at physics@vernier.com or give us a call, chat with us online. However you want to reach out, we're here for you. All that being said, I will pass you off to our presenters, and thank you so much for joining us.
Thanks, Dylan. Tom Smith here. Let me catch up my slides. Dylan's already gone over a lot of the housekeeping issues. Just make sure that we didn't miss anything here, Dylan. Looks like everything's good. There is an email address for KidWind@vernier.com there. It's good to note if you have specific questions about KidWind. And with that, I'll briefly introduce myself. Tom Smith. I'm part of the engineering education group here at Vernier, and a recent addee to the KidWind group. I've been a fan of KidWind for quite a while, and now I get to play with it on a more frequent basis. And as Dylan mentioned, Fran's with us here today. Fran, do you want to introduce yourself?
Sure. First of all, I love, Tom, that you said a fan of KidWind. Very nice. Yeah, so my name is Fran. I am the director of physics here at Vernier, and I'm also the technical lead on our KidWind line of products. So you can also ask me anything KidWind. And again, that email address, kidwind@vernier.com, will get to the whole KidWind group. Whoever's the first one who is available to pick up your question will answer you, and you should get a quick response.
Excellent. Okay. With that, let me just introduce kind of our general agenda. So with KidWind, it's a great platform for introducing the engineering design process, which is our primary focus for today. But for myself, as I was going through preparing for this webinar, I started to look at how the engineering design process meshes together with state science and engineering standards. So I'm going to spend a bit of time talking about those. Going to introduce the KidWind equipment that I'm focusing on for this, the KidWind Basic Wind Experiment Kit, as well as diving into some of the details of the blade design activity. That's part of our renewable energy book. That activity you'll find in the materials that Dylan's sharing with you in that shared folder. And then in addition to that activity, I've basically taken it and modified it to focus on engineering design principles. And I put that in that shared folder as a Word document so that you can take it and modify it. I will mention that this is a Tom Smith modification. Not you won't find that anywhere in any of our books or anything like that, but I thought it was worthwhile going through the process of just highlighting where those engineering standards might fit into that particular activity and how you might modify that to do that. Let's see, we'll go ahead and jump ahead here. So why are you here in the middle of your summer vacation? I'm guessing that some of you might teach engineering either at the college or high school level and are seeking some relevant activity to kind of expand or put into practice the engineering design principles. Or you might teach science and need to figure out some way to integrate those engineering standards. If you're a high school or middle school teacher, have to figure out how to integrate those engineering standards into your science curriculum. Whatever the case is, we think KidWind is a great platform for accomplishing this. It is a really tangible and relevant activity working with renewable energy, something students are eager to engage in. And we find it is applicable whether you're, again, in middle school or in high school or on up into the college introduction to engineering type courses. We're seeing it used quite a bit there. So we hope that's why you're here watching this today. So I want to start off by talking a little bit about the engineering design process. If you were to do an internet search for the engineering design process, you'll come up with a myriad of examples. Typically, it's presented as kind of a cyclical process where you start in one place with understanding what your problem is, and you go through a series of steps and then execute a solution and then check that solution to see how you did. And then you might have to go back and do it all over again to make sure you're getting the results that you expect or your customer intends for, has placed that expectation on you. You will find examples of this process ranging from as simple as 4 steps to as complex as 12 or 15 steps. My experience with this is that Personally, I can remember 4 things in a row. So I've kind of committed the simplest version of this to memory: plan, do, check, act, which I presented here. But I acknowledge that the more complex systems that are out there, they all kind of plug into this same criteria: plan, do, check, act, just multiple steps in each one of those activities. As I mentioned, most of these are presented in kind of a cyclical fashion. Some of them are much more like a computer flow diagram, where you go through a few stages kind of in common, and then you have feedback loops depending on the results that you're finding in your analysis stage, in your checking stage. I'm going to refer back to plan, do, check, act several times during the webinar, so you can just kind of keep that in mind as we're going through this. For those of you who teach high school or middle school students, your state standards probably have engineering practices identified in them. And I have outlined a few of these that we're going to be engaging with in this activity: asking questions and defining problems, planning and carrying out investigations, analyzing and interpreting data, and constructing explanations and designing solutions. Now, the activity that I've modified, the blade design activity that I've modified for engineering design principles, tries to attack each one of those practices. It may be more than you want to take on in a single activity. That's why I gave you the Word document, so you can modify that as necessary for your particular needs. When I first got started with this, I expected the engineering design process over here to mesh very nicely with these engineering practices that are outlined in most of your state standards. What I found, though, instead of this type of a scenario, was kind of like a mesh, where the engineering practices overlapped several parts of the design process. So, for example, if you're looking at analyzing and interpreting data, that might occur in the planning stages, but it also might occur in that checking process where you're evaluating your results to see if you were in fact effective at accomplishing your goals for the engineering activity. So it's kind of an interesting discovery on my part, and you can bear that in mind as you're kind of teaching 2 things. You're teaching the engineering design process on one hand, and you're integrating those skills, those practices, on the other hand, for engineering practices. We will come back to these again to talk about specific elements of each of these that I've highlighted in the activity that I've created. I want to turn to the KidWind turbine, just to identify kind of what those parts are. I have one sitting on the desk here behind me. It has a tower, key part of it. It has a nacelle, which is just a fancy word for the gears and generator that are housed in this portion of the wind turbine. And then we have, of course, this hub and the blades that are attached to the hub. Our KidWind towers are designed to be driven by a box fan, which you can see in the background here. Or we also have a wind tunnel that is larger and has more uniform airflow than a basic box fan. Typically, when we are recommending this for a classroom, we have this set up with materials for designing blades up to 8 lab groups, if you will. But we only provide 3 towers. And the reason for that is that if you imagine a classroom full of 8 towers and 8 box fans all blowing at the same time, you can imagine there's a bit of chaos. The airflow is maybe not uniform at all. And so it just seems to work better having 3 testing stations, and then multiple lab groups can do their work at their lab stations, and then take the hub and blade material and take that to their lab station to modify the blades however they want to, and then come back and test it on the at the station there. We also, and I'll point this out in a second, include or would recommend some sensor for data collection, and in particular the energy sensor that's really designed around the KidWind product. Has a built-in resistor, but we also sell a variable load resistor, which provides some additional flexibility and testing criteria there. So let me spend a few minutes talking about the basic blade design activity in our renewable energy book. And I'll see if I can change my camera view here to give you a little bit better picture of that. Here, by the way, is our energy sensor. It has, again, a switch. You can either have an external resistance applied, or you can use the internal resistor that's built into the energy sensor. Running a wind turbine without some sort of resistance or load is akin to riding a bicycle in first gear down a hill. You just don't you don't feel that resistance. You're not generating any energy into the system. So the blade design process is really as it's designed in our renewable energy activity, designed around this hub and basic blade design materials. This is just a chipboard. It has a wooden dowel that we've glued the chipboard to, and the wooden dowel fits into this what I think of as a tinker toy type of clamp. You can just untwist the screw here and adjust, see if I can find the camera again, adjust this. You can have a different number of blades. You can orient the blades in different directions. If you were going to do 4 blades, you might put them all at 90 degrees to one another. You can set the angle as well with that. The blade design activity really focuses on a couple of prescribed sets of experiments. One would be the number of blades. So you can, again, there's 12 holes in this hub. You can put 12 blades on it with some challenges for space, I might add. You can put as few as 3 or 2. If you get into some odd numbers, you'll find it difficult to make it symmetrical. But you can do 2, 3, 4, 6, 8, and 12 without too much difficulty. So you can go through quite a range of the number of blades that you're working with. The next thing you might test is the length of the blades. So we have, blades that are going to be shorter. Again, see if I can find my camera view there. Shorter or even longer. Let me see that there. We have the length of the blades, the number of blades, the angle at which the blades are set, which is called the pitch. And I'll just demonstrate this tool if I can. I have a protractor that a customer basically designed for us. And his name is Niels Anderson on the back of the blade or back of the protractor. We give credit to him every time we sell one of these. And basically you just line that up onto the hub and read down, there we go, down the angle here. So you can set that protractor to, or set the angle of the pitch of the blade according to the protractor so that you get a uniform angle for the various blades, but you also get the chance to alter that pitch to see what the effect is of the pitch. So then we have the number of blades, the length of the blades, the pitch, and then you can experiment with different shapes. So here we have something that looks like a feather. We have a blade that is truncated at the close in to the center of the hub. We have another one here that's more, again, just a little rounded on the outside, square on the inside next to the hub. And you would run all of those types of materials with measuring the power output from the wind turbine. And that's pretty much just prescribed in that activity. We provide that, there's not a discussion about what you're going to measure, but rather just providing the students with that indication of that's the measure of efficiency that you're going to be looking at for energy production from a wind turbine. And we're going to talk about how this gets modified for an engineering design type of activity. So where this is all kind of laid out for students in a science course or a renewable energy, environmental science course, we're gonna poke at that a little bit for the engineering design aspects of this. Okay, so if we revert back to the engineering design process, these four practices that I've identified, I pulled out specific elements from state standards relative to each one of these. So in asking questions and defining problems, the particular element that we're going to look at is to clarify the problem we're looking to solve. So our questions are going to be focused on, what is it that we're trying to accomplish and how do we do that? Planning and carrying out investigations, clearly part of the planning stage, but also looking at how much data do we need? What types of data do we need? Is there a measure of accuracy we need to be concerned about with the measurements so these are the questions that the engineering students are going to be faced with answering rather than just being given as part of a science activity. And under analyzing and interpreting data, making quantitative claims regarding the relationships between dependent and independent variables. So really looking at the data that they collect and understanding what that relationship is. And then finally, under constructing explanations and designing solutions, this shows up both in the planning stages and in the final, the doing and checking portions of the plan, do, check, act engineering design process, where they're trying to explain the phenomena that they're observing in their testing and applying that explanation to design a solution, and then analyzing the data to determine what their optimal design solution is. Okay, if you're thinking about doing this as an engineering activity, rather than just providing them a wind turbine and a lab handout and letting them go to work, you might start by just having a discussion about how have wind turbines evolved over time? I throw these pictures up here as kind of a prompt for students to think about, okay, what are the purposes of these particular windmills? How are these similar or dissimilar? What are the characteristics that are unique to each of them? And just having a discussion about, okay, what's the purpose of each one of these activities, rather than just jumping right into the blade design activity right away, thinking about uh, uh, how different parameters or characteristics of each of these turbines may be fitted to the particular purpose of the turbine. So, and then thinking about those clarifying questions, what is the goal of our particular wind turbine? What are we trying to do with it? Well, we're trying to produce energy. What is the right measurement of energy production? This typical Dutch windmill and this windmill that you might find in the Western United States are really designed for moving water, for pulling water to the surface or pushing water over a dike. And they weren't concerned necessarily with just the volume of water, but it was really the volume of water over time. So this might be a way to introduce the idea of power versus just energy production. So power output being energy, the rate of energy production is kind of the key measurement that we want to drive towards. But to have that discussion with the students to kind of get them to understand why we're measuring power versus just energy production is kind of a key part of this clarifying questioning. And then using these as examples, looking at the design factors that are going to affect efficiency. Certainly the number of blades pop out here. Some other factors may be less obvious. You can look at the length of the blades here. You can look at, you can kind of get to angles of the pitch of the blades, but, this is a point where you might send your lab teams into separate groups to come up with what are the design factors that they need to consider. Maybe bring them back together to share as a class so they come up with a common set, or maybe leave that to the individual lab groups and have that be part of their challenge, is to identify what they're going to evaluate to come up with their best design. In the step of the engineering element for planning and carrying out investigations, we have plan and investigation for testing solutions and determining the data types, quantity, etc. And I find that this is pretty intuitive for students to figure out, okay, we're going to test the length of the blades or the number of blades, but coming up with a strategic approach for that may be a little bit of a challenge. If they have limited supplies, they don't want to test the shape of the blade before they've tested some of the other factors. So they'll need to think about that. So again, this may be something they design individually as lab groups. You may need to reinforce the idea that they need to be cognizant of testing one parameter at a time and keeping the other elements of consideration constant through that testing, rather than just kind of randomly changing things as they move along. One thing that they, if they come up with 4 or more characteristics of their blade design that they're going to test, one thing that they may not consider is just the complexity of that matrix of testing that is available to them in that case. So when we do this activity as a outreach to local schools, we typically have them do it in this order, where they test the number of blades, and then they take the optimum number of blades from that, and they test the pitch angle to see what gives them the optimum pitch angle, and then move on to blade length, or those might be reversed, I forget. And then finally, the shape of the blades. But if what I've noticed from my own personal testing is that let's say that my optimum number of blades in this test is 3 based on this set of constant parameters on the other factors. If I come here to test pitch with 3 blades, I will get a result that gives me an optimum, but I might also find that I get a slightly different result if I look at 2 blades or 4 blades. So there is, if you have the time, the luxury of being able to build a longer activity out of this, to have them do, encourage them to do more testing than just finding the optimum of one, moving on to the next, and so forth. But really exploring, maybe bracketing what their optimum was here, going to the pitch, and then bracketing maybe 2, 3, and 4 at all these different angles to see if they actually get a better solution coming out of 2 blades or 4 blades at a different angle. So again, this can get as complex as you have time for, or keep it simple and just drive them through a series of steps there. Under analyzing and interpreting data, so you're going to try to make quantitative claims regarding the relationship between dependent and independent variables, and then analyzing those claims to drive that optimal design. Some questions that they should be asking themselves at this stage are, of all the data they collected, do the data make sense? Have they identified gaps in the data that require additional testing? That one's a little bit easier to identify. Do the data make sense? They may have a case where there's an optimization where maybe the number of blades provides better values for power output as you increase, but at a certain point it drops off. And if there's a scenario like that, it may be very worthwhile having a prompt for them to try to understand why that's the case, to come up with some hypothesis of, well, maybe at some point the weight of the blades provides more inertia than the wind can overcome, for example, or just having them kind of noodle a little bit about not only what the data are, but why they suspect that might be the case. And then we get to constructing explanations and designing solutions. This is really where the fun occurs. So, don't be a killjoy. I can remember several times in my teaching career when we would have an activity like this where the kids were really excited about doing something with it. And I would be intent on driving home one technical point. And in the process of doing that, I would just suck all the life out of my class. So I would encourage you to step back and allow the kids to have their joyful moment of testing their turbine blades and seeing how they do against their other lab groups in the class, or whatever that is. I'd also like to have you consider whether you want to encourage the competition model, which is a valid model. A lot, students love a good competition. Or you might also consider this collaboration, where we've had college professor who did outreach with a local school, who instead of really reinforcing the competition mode, they looked at how much energy can we create together. So they would just continue to add all the energy together till at the end of the day they celebrated how much energy they created using a renewable resource of wind energy. So depending on your scenario, you might find either or both of those useful models to consider in the process. So that's kind of my take on the incorporating engineering design principles into this KidWind activity. Again, I'll encourage you to take a look at this resource that's in that shared folder, which is my take on addressing those engineering standards throughout the activity. And you'll see those just kind of bracketed. For example, under planning, I have in a bracket at the top of that unit, clarifying the problem you're trying to solve. So modified the questions around that to try to drive those engineering practices into the activity a bit. So I encourage you to take a look at that. Some other things to consider, you're not limited to using chipboard. You might have them, if you have a 3D printer available, look at 3D printing blades. I actually have an example of that. If you do that, know that weight is going to be a consideration. So you'll be considering fill patterns for, can you make this strong enough without making it a solid piece of plastic? That reminds me, there is a news, a bit of information in the news today about wind turbine, offshore wind farm that lost a turbine, and the blades ended up getting washed up on the shore somewhere in, I think, New England, if I'm not mistaken, Massachusetts or Rhode Island. So again, making this a relevant topic for consideration, designing the strength of the blades is an important aspect of this. You might also have them just use recycled materials. There's a number of kind of design constraints that you can put on this to drive their solution one way or the other. We've had a number of colleges ask for alternatives that kind of prevent sharing solutions from year to year. So if they use the same activity for an engineering design, introduction to engineering design course, they start to see a lot of duplication from year to year as students figure out how to share solutions from previous years. So coming up with some different constraints to modify that activity from year to year can be valuable. You might have them experiment with different wind speeds or different gear ratios for the gear to the generator from the wind turbine itself. This is adjustable, so if you get a smaller gear up here, you can move it up. You might have them experiment with optimizing the gear ratio for given wind speeds. So there's a lot of different variations we can work with there. Some college activities have also included building a base to withstand high winds. So they, instead of giving them a tower, they were given the nacelle and the hub, and then they were told to design a base for that particular activity, whether it was just winds in our central United States, where we have can have some high wind patterns, or building a floating platform to imitate, some of the offshore wind farms that we have around the United States, both on the East Coast and more recently some design efforts on the West Coast, which have their own particular challenges because they're more typically going to be floating on the West Coast due to the depth of the ocean where there's good wind patterns, as opposed to being able to actually anchor a wind turbine offshore on the East Coast. You might also, if you have the resources, actually have them build the nacelle that's going to enclose the generator and the gear structure there. So lots of opportunities for modification there. And at that, I will pause and see if there are any questions we need to address from chat, or see if there's anything else out there that you're curious about.
So in the chat, there was a question about grants, and I don't know if you know of any, Tom. I suggested the possibility of one school PTO, and then also some states with a lot of wind energy industry also may have some state money, like New Jersey, for example, is one of those. Or the energy company itself may have designated money for schools, because some organizations do have designated money for that.
Yeah, absolutely. Fran, I thought you said France, and I was like scrambling desperately to figure out what France would have to do with this particular activity, but grants, absolutely. So when I was teaching, there are a lot of technology companies that offer grants, like Toshiba is one that I was successful in getting a grant money for, especially if I was teaching STEM activities. So you might research those. Certainly investigating companies that are involved in wind energy. We have a local company, Vestas. Well, it's not local, but they have a local presence here in the Portland area that are designed in or engaged in wind energy. Trying to think if there's other, it might be worth reaching out to in those areas where wind energy is prevalent, reaching out to like community colleges or colleges to see who they have partnered with for grant opportunities, to see if there's a potential connection with either with the college itself or with the companies that they're able to partner with as well.
And then we had another question about experiments that test wake effect and or just simply involve more than one turbine. To my knowledge, we don't. You can certainly challenge students to create a wind farm and connect up multiple turbines to maybe store energy in capacitors or in batteries. But no, we don't specifically have ones about that.
One thing I have done is experiment with the wind pattern from the box fan. So I've taken our anemometer from our weather sensor and just somewhat methodically tracked from the distance, and then also cross-sectional to understand how that wind is affected by distance. So there, you may be able to optimize the location of your wind turbine based on some experimentation around that as well.
Yeah, I'm just going to stick a link for that in the chat.
Awesome. Well, anything
those are
else?
Those are all the questions that I see so far.
Okay. There's a list of product links that is included in the slide deck that is also in the shared folder. So that's a resource available to you. The Renewable Energy with Vernier lab book, for those of you who don't win it today, is a good resource for looking at additional criteria that you might consider when you're creating an engineering design activity around this. There's
Tom?
Yeah.
Another question came in about, does the kit have different gears, or can we install more gears?
So I guess the answer to that question is yes to both of them. Now, Fran, you're more familiar with the kit. What actually comes with the basic or advanced kit for gearing?
So there's actually a total of 4 gear pieces. There's a 8-tooth pinion gear, which is placed directly on the generator. That's a little tiny one. And then there's a 16-tooth gear, a 32-tooth gear, and the 64-tooth gear. And the 64-tooth gear is right there on the nacelle that Tom has constructed.
Yep.
And then um, the patterns for those gears are actually on Thingiverse. So if you go to Thingiverse, THINGIVERSE, and search for VST, that's or KidWind, you should find the pattern for the gears, which will give you the pattern that it needs to like fit in our Hub Quick Connect. And you may be able to adjust those to different numbers of gears besides those. And certainly students who participate in the KidWind challenges, I've had the pleasure of going to a number of the national challenges, and kids make all kinds of gears. People do belt drives, they do like giant gears that are 30 centimeters across or more. They do a whole variety of things. They create elaborate gearboxes too sometimes. So certainly if you give kids the time and the opportunity and the challenge, they will come up with stuff.
Absolutely. So
oh, and then a power output question. So the typical range of outputs varies dramatically, but it tends to be much less than 1 watt, especially at the beginning. But the typical, so that the sensor is measuring actually just straight up voltage and current, and then it calculates the power and total energy produced. And for experimentally calculating the efficiency, you're going to need to know the density of the air and the wind speed, and then there's a formula that you can just look up. So that gives you the amount of energy that's present, amount of power present in the wind for a given wind speed and air density, and then you'll have to look at the power output and do the percentage. But I think we're about done.
Yeah, Dylan, did you want to say anything about are we going to have the drawing now? Is that the next step here?
Yes, absolutely. So everyone who is currently online, I have entered your names into a random name generator and selected today's winner. You'll be winning a Renewable Energy with Vernier ebook. So we'll go ahead and email that to the email account that is associated that you signed up for this webinar with. And the person who won is David B. So congratulations, David. I'm going to go ahead and email you that information. So keep an eye on your inbox and congratulations. And I did want to say, Gary, I see your question in the chat. We are giving a certificate of attendance. Every district is different with what counts and what doesn't count, but you will get what we can offer in the resources folder that are linked above. So, yeah. Thank you all.
Well, yeah, thank you all for coming.
Yes.
Appreciate your attendance here in the middle of the summer. And feel free to reach out to us at kidwind@vernier.com if you have further questions.
All right. Happy Thursday.